Hi, I've been trying for the past 5 to 10 minutes. It is not connecting me at all. And hello, I don't know what's the next. Hi, students. Yeah, sorry for the delay. There has been a small network issue from my side where it couldn't connect. It's been connecting and getting disconnected. Nevertheless, let us start today's class. I hope some people are still there who's actually waiting. Let me see how many of you people are actually waiting. So, fine. Good evening, and are actually waiting. Fine. Fine. Good evening, and are actually waiting. Fine. Yeah. Let us now, you know, get into the details of the memory where we start in the last day, in the last week or the previous week class when it happened exactly. I don't know, but let me tell you that today I am going to take you people into the next step into the cache memory. Let us do that. Say hi if you have anybody there, or say hi, my regular people. There has to be at least 3 to 4 people are regular to my class. I just want to see them. Fine, anyhow. Um, yeah. Now, in today's session, we will focus on various mapping techniques in cache memory, for the cache memory. When it comes to the cache memory, you people knew that there will be an address space difference. That is, main memory is huge and the cache memory is smaller. I hope you got it. That is, let me draw here. Usually, of course, any time when we talk about, when we consider memory, that memory will be more greater than the cache memory. I will show you here. Okay. Yeah. Consider this is the cache memory. Stay focused. Consider this is the cache memory. And this is main memory. Stay focused here. Now, let me give you an example through which the mapping techniques can be completely understood. Okay. Let us take a main memory in a system which is equal to 32K. Okay. If it is equal to 32K, the number of address digits for the main memory is equal to 15. I hope you got it. Because 32K is equal to 2 power 15. Right? There are a total of 32K locations. in the main memory. Okay, which means that each and every location needed an address length which is equal to 15 digits. So memory will be addressed in between 15 zeros to 15 ones, right? So the address length of the main memory is equal to 15. Now, when it comes to the cache memory, the system also has a cache memory which is equal to just 512 words. Just 512 words. Okay. Now, the cache memory requires 9 address digits for addressing any location. That means that the cache memory can be addressed by using 9 zeros to 9 ones. Okay, I will use an octal address mechanism to distinguish. So the cache memory first address will be 000 in the octal because the address length will be equal to 9 zeros. 9 D zeros will be simplified by using 3 zeros in the octal number system, and at the same time, the final address will be equal to 777 because final address range is equal to 111, 111 and 111. So if we simplify in the octal, this 111 is equal to 777. So the cache memory will be addressed by using 9 digits and the main memory will be addressed by using 15 digits. When we simplify, we'll get 3 digits in the cache memory, we'll get 9 digits in the main memory. So it will be 5 digits in the main memory. 1, 2, 3, 4, 5 is the first location. 1, 2, 3, 4, 5 is the first location, and 7, 7, 7, 7, 7 is the final location. Okay. Now here, let us understand when CPU tries to communicate, it is going to send 15-digit address reference because CPU always communicates with the memory modules by using an address length which is equal to main memory address length. So CPU always communicates with the main memory address. Let us say now the CPU wants to search for an element which is in 20000 location octal. Okay, which is if we translate into binary, it will be 010, 000, 000, 000, 000. This is the address length. This is the address that has been released by the CPU. This is the address that has been released by the CPU, in which it is going to access the element. But you know that whenever CPU releases any address, this address will have to be searched within the cache memory. Okay, whenever CPU want to access any element, first of all a search will be made within the cache, right? So taking this address, CPU doesn't go to the main memory directly. For this address, a search will be made in the cache. But here the problem is the address length of the cache. The address length of the cache is not equal. Both are not equal because here we do have 15-bit, here we do have only 9 digits. So here there is a problem. So here what we need to do is we need to map the reference address of the CPU to the corresponding address within the cache memory. In other words, CPU sends a 15-bit address that should be mapped to the corresponding 9-digit address within the cache memory. How we do that? So let me tell you. There are 3 ways that we can do this. This mapping mechanism can be realized by using a few mapping techniques. There are 3 mapping techniques that can be used by the CPU. Okay, different designers can go for different mapping techniques. These mapping techniques are, the first one is an associative mapping. Second one is the direct mapping. And the third one is the set associative mapping. Okay. Today we will talk about the direct mapping procedure. How? By using the direct mapping procedure, the address length which is referenced by the CPU will get mapped to the corresponding address length which is available at the cache memory. Here the problem statement is very clear. CPU will communicate with 15-bit address. Okay, because main memory total address length is equal to 15 digits, right? But taking this 15-digit address, CPU will go to the cache first, because initially a search will be made within the cache for locating this address. But the problem is our cache memory is of just 512 words, which has an address length which is equal to 9 digits. Okay, so what can be done at this point of period is we can use one of the address mapping techniques, in which this 15-digit address length will be mapped to corresponding 9-digit address length. Okay. This is the cache memory. It is addressed with 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the first address of the cache memory. 111, 111, 111. This is the final address of the cache memory. At the same time, system has a main memory which has an address length which is equal to 15 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is the total address length of the main memory. Here you can clearly see that the address mismatch. Now what we'll do is, we will use the direct mapping technique to map the reference address of the CPU into the corresponding address of the cache memory. Now let us say CPU referenced an address which is equal to 010, 010, 010, 011, 000. This address reference has been sent by the CPU for accessing the corresponding data word. So CPU sends this address reference. This address reference will be searched within the cache. For this address reference, a search will be made within the cache, right? But how? The address reference is equal to 15, but we do have only just 9 digits. So here in the direct mapping process, first of all that you need to understand this, at every location we do have two fields. For every location we do have two fields. One field is the word field. This is the regular word. Okay, we are not affecting this word. This word is either 16-bit or 32-bit according to the architecture. This is the word. Okay, if the address is matched, this word will be read by the CPU. Okay, so in addition to this word field, we do have one field called tag field. We do have a field which is called tag field. Now let us stay focused. The reference address by the CPU will actually be divided into two parts. I will write it here as the space is not sufficient. CPU reference address is 010, 010, 000, 000, 00, let us say this is 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, now this total address reference, before it gets located in the cache memory, will be divided into two parts. One part is called common portion. The other part is called remaining portion. Let us stay focused again. The total address reference will be divided into two parts. One is common portion, which is common for both cache memory and the main memory, and the remaining portion. This remaining portion is not available in the cache memory, only it is available in the main memory. So this is how this address will be divided. Okay, this common portion can be called as an index, and the remaining portion can be called as a tag. Okay, now you can clearly see that this portion, which is equal to 9 digits, you can locate it in the cache memory, because cache memory has a 9-digit address, right? this portion can be located within the cache memory because the least significant 9 digits are available within the cache memory. This least significant 9 digits, whatever the value it is, can be located within the cache because the cache is of just 9 digits. Okay, which is equal to 9 digits. So there is no problem of locating this index portion within the cache. Within the cache. Just let me see. Within the cache, right? Somebody there? Yeah. Now, I presume this portion is available within the cache. Then this will get located. Okay. After locating this, then there is a tag field inside. Did I make it myself clear? As every word at every location has an additional field called tag. After locating this least significant 9 digits, then the next job is to compare the available tag at the location with the reference tag in the address. This is the thing that is going to be done in the direct mapping procedure. That is, again, understand the steps. This is the address reference that is released by the CPU. Before it gets located in the main memory, it will have to be located in the cache memory. Because every time we are going to perform a search within the cache for any hit. But cache memory address reference is less. So what we do is, total address length will be divided into two parts. We will divide the total address length into two parts. One is common portion, which is common in between main memory and the cache memory. In this case, the least significant 9 digits, and the additional memory. The additional digits. This common digits is called as an index portion, and the remaining digits will be called as a tag portion. I hope you got it. Now the index can be located. After locating the index, the next step that is needed to be performed is comparing the available tag with the reference tag. So let us say here there is a tag which is equal to 010 010. Did I make it myself clear? Now you can clearly see that these both tags are equal. When the both tags are equal, then that means that the cache produces a hit. You can read the word. Did I make it myself clear? You should be very careful in listening to this because this is one of the important topics. That is mapping procedure. Once again, why mapping procedure? Mapping procedure is seriously needed because every time when CPU references an address, that address reference will go through the cache to the main memory. But when it goes to the cache, there will be a mismatch, address length mismatch. In that case, in order to map the main memory address with a corresponding cache memory address, we require a mapping technique. In this case, we are going to use direct mapping procedure. In the direct mapping procedure, total address length is divided into two parts. One is the common portion. Common portion is called index. Index is available, located. And then compare the reference tag with the available tag. If both are equal, hit, read the word. If both are not equal, miss, don't read the word because the word that you are searching for is not available in the cache memory because tag is mismatched. Tag is not compared. Okay. So at that time, whenever there is a miss, what we do is directly we'll go to the main memory, taking the total address. Of course, in main memory, we can locate the total address because main memory address length is equal to 15 digits. So whenever there is a miss in cache, what we do is we will go to main memory. We will read the complete word. Okay. And CPU reads the word directly from the main memory. At the same time, the CPU will have to send this word also to the cache memory for the future references. This is already, you people know that several times I also told you people that whenever there is a miss within the cache, we are going to collect the word from the main memory. At the same time, we also should send this word to the cache memory for the future references. Because if a word has been accessed right now, that word may be accessed in the near future. This thing is called locality of reference. According to the locality of reference phenomena, the word which is currently accessed needed to be transferred to the cache memory. So that's it. But where? Under the same index, replacing the previous tag with the current tag and replacing the previous word with the current word. That's it. So during case of a miss, CPU directly reads the word from the cache memory, from the main memory. As it is reading from the main memory, parallelly this data word will also be transferred to the cache memory, where in this, under the same index, it will replace the previous tag with the current tag. It will replace the previous word with the current word. This is the direct mapping procedure. Once again, let us list out the direct mapping procedure. Now, divide the address into two parts. As index plus tag portion. Okay. What is index? Index is number of bits to represent cache. What is tag? Remaining MSBs. Okay. So likewise, we are going to divide this address length into two parts. One is index portion and one more is tag portion. Okay. Now, based on this, what we'll do is, we will solve a few questions in Gate. Okay. It is very easy. Once after you understand, we can solve any Gate questions. Let me give you a question by myself so that you will be able to answer. Now let us stay focused here. Okay. I will give you a question by myself. A CPU uses 32-bit addresses. 32-bit addresses. Any doubts in this? If you can ask me, so that I'll be able to answer your doubts, so that I'll be able to process to the Gate questions. A CPU uses 32-bit addresses. It has a cache memory. Of size 32K. What is the number of digits in index portion and tag? So this is the question. Here in this case, a CPU uses a 32-bit address. Okay, and let me add one more point here. The cache is direct mapped. It's a direct mapped cache. A direct mapped cache memory of size 32K used in the system. Okay, what is the number of digits in the index and the number of digits in the tag? Let me show you how it is going to be divided. The address length is equal to 32-bit, right? The address length is equal to 32-bit. If it is a 32-bit address, okay, how the division is going to be made? Now, you know that it has to be divided into index and a tag. Okay, what is index? index is the number of digits that are required to address cache, right? Here, what is the cache size? What is it? The cache size is equal to 32k. If it is equal to 32k, then the number of digits that are required to address cache is equal to 15, because 32k is equal to 2 power 15. So total 32 will be divided into two portions, where index is equal to 15. You know that the index is common portion between main memory and the cache memory, right? So the cache memory is equal to 15. So the common portion between main memory and the cache memory requires 15 digits. In addition to the 15 digits, we do have a 17-bit tag. Okay, so the index is equal to 15, the tag is equal to 17 in this case. I hope you got it. Okay, so this is how you are going to divide index and tags whenever you are asked to divide index and tag in the direct mapping technique. Okay, now stay focused once again. There is something called set associative mapping also. Okay, this is the second mapping technique. I will take you to the set associative mapping theoretically, but before that, let me enhance this previous question to set associative mapping. What if this question is revised as a set associative mapped cache? A set associative mapped cache, if the question is asked in such a way that if the cache is designed as a set associative mapped cache, then what is the number of digits for index and tag? Same thing, the question remains the same, only there is a small difference. The only difference is which in the previous case the cache was designed by using direct mapping technique. In this case the cache is designed by using set associative mapping technique. Okay, now in this case what is going to be done is, when it goes to set associative mapping, stay focused carefully. The procedure will be one and the same till you divide the index and tag. Index will be equal to initially 15 digits and the tag will be equal to 17 digits. But after performing this division, then what we do is, we will just do a small additional step, that is, index will be equal to index minus 1, tag is equal to tag plus 1. This is the simplest technique that you can ever hear, that you can ever listen to while you solve any questions that are asked when it comes to set associative mapping technique questions. Okay, once again, how to solve when a question asked based on set associative mapping technique to divide the fields of index and tag. What you have to do is, you just go for the normal procedure how you divide the index and tag as in the direct mapping technique. So index will be equal to as many number of digits as they are required to represent the cache, and the tag will be the remaining digits. So in our case 15 and 17. But hold on, these are only for direct mapping. But what if the question is talking about the set associative mapped cache? Then what we have to do is simple. You need to subtract one digit from the index, and the subtracted digit should be added to the tag digits. Simply, in other words, index is equal to index minus 1, tag is equal to tag plus 1. Tag is equal to tag plus 1. Okay, so here the total number of digits for what do you call index is equal to 14 and tag is equal to 18. This is how you divide index and tag in set associative cache. Now, this set associative cache, whenever you come across a term called set associative, you need to imagine or assume that this is a two-way set associative cache. Two-way set associative cache. What is this two-way set associative cache? Stay focused here. What is this two-way set associative cache? The cache, every cache address has two locations. Simple. You write it down somewhere. In two-way set associative cache, every cache address will have two locations. Okay. Now, there can be a four-way set associative cache also. In four-way set associative cache, you can say that every cache address has four locations. If it goes to 8-way, as you rightly interpret, every cache address has 8 locations. Okay. So this is how you need to imagine, rather you need to assume how associative cache is going to be designed. When it comes to two-way set associative, every cache location will have two words. Four-way, every cache location has 4 words. 8-way, every cache location has 8 words. 1, 2, 3, 4, 5, 6, 7, 8. Okay. This is either two-way or four-way or 8-way. Now let us solve another question which is based on direct mapping and set associative mapping. If you do have any doubt so far, just please ask me. I think you people are lately joining. I don't think that you get something. Rather, what you do is just once after I finish the class, you just revise this class once again. And these classes are already available. When last week also I think I explained you about the cache memory. So what you people do is you just have to go through my previous classes, so you'd be understanding continuously and in a better manner. Now again, just what we do is we'll solve another question which is based on direct mapping. In this case, let us say that CPU uses 24-bit address. A CPU uses 24-bit addresses. A four-way, in order to reduce the complexity, I will say it as a direct mapped cache of size 8K is used in the system. Rather, 4K is used in the system. Find out the number of digits in index and tag positions. Okay. Now what we have to do is, again we will go with the same procedure. We will have to draw a 24-bit address here, 24-bit address here. This 24-bit address will have to be divided into index and tag, right? What is index here? Again, the index is equal to, let us stay focused. Index is equal to number of digits in cache, number of address digits in the cache. Did I make it myself clear? Number of address digits in the cache. Okay. So here, number of address digits in the cache will be equal to, let us look at the cache size. Cache size is equal to 8K, 4K. If it is 4K, number of address digits in the cache is equal to 12. So, out of 24, 12 bits will be for the index. 12 bits will be for the index. The remaining 12 digits for the tag. I hope you got it. CPU uses 24-bit address in which 12 digits will be in the index field and the remaining bits will be in the tag field. This is how it is going to be done. This is how it is, the division process is going to be done. At the same time, it is quite evident that from the discussion what we had, when we go to set associative mapping procedure from this, index will be equal to index minus 1. Tag will be equal to tag plus 1. In such case, tag will be equal to 13, index will be equal to 11. It is for two-way set associative mapping. Okay, I hope you got it. Now tell me, what is four-way set associative? When you go to four-way set associative, if you can actually understand, index is equal to index minus 2 from direct mapping, tag is equal to tag plus 2 plus direct mapping from direct mapping. That is index is equal to index minus 2, tags is equal to tag plus 2. Okay, there are two-way set associative mapping, 4-way set associative mapping, 8-way set associative mapping. Every time the associativity is getting increased, index will be reduced by 1, tag will be added by 1. Okay, so when it comes to 4-way, index is equal to index minus 2, tag is equal to tag plus 2. I hope you got it. Okay, so that is in the 4-way set associative mapping, index is equal to 14 and the tag is equal to 10. Finally, we need to get the total number of address digits that are equal to the referenced address digits by the CPU, in which case it should be equal to 24. I hope you got it. Okay. Now, sometimes, rather, most of the times, the question will also have another part, that is the block size. Block size. Okay. Now let us say that the above stated question has this statement as an additional statement of the block size. Okay. The block size is 32 words, let us say. The block size is equal to 32 words. Just simply understand, this is nothing complex. For the above mentioned question, there is an additional statement, that is, in addition to whatever the statements that are written, that is the CPU releases 24 bits and the cache has size of what do you call 4K. Find out the index and tag fields, and in addition to that, they mention a block size. When the block size is mentioned, in what way we need to solve the question? When the block size is mentioned, we will be asked to find out the number of digits for the tag and index, and also for the word field. Okay, also for the word field. So here in this case, let us say our block size is equal to 32 words. Okay, now once again consider the question. Address length is equal to 32 bits, sorry, 24 bits in the above case, in the above mentioned question. Cache size is equal to 4K and the block size is equal to 32 words. Yeah, somebody is filling this with a hi. Of course, hi, but better you focus on the class rather than simply typing the messages. I hope you joined late, but what you do is just if you can see back, you will be able to understand completely. Okay, now 32 words. So whenever a block size is given, what we have to do is the total address will anyhow be divided into index plus tag. Anyhow, index is equal to, what is index? Index is equal to as many number of digits as required to address cache. Cache is equal to 4k. So the number of digits for addressing cache is equal to 12. Index is equal to 12. And the remaining is equal to tag, right? Tag is equal to 12. So, but when the block size is given, what we have to do is the index part will be further subdivided into two more portions as index and word fields. Okay. So, what is this index and word fields? Anyhow, tag is equal to 12. Index is equal to 12. This index will have two parts whenever the block is mentioned. So, whenever block size is mentioned, this block size requires a few address digits. How many? As the block size is equal to 32, the number of digits that are required to represent the block will be equal to 5, since 2 power 5 is equal to 32, right? So, I do require 5 digits. So, what you do is, these 12 bits will be divided into two portions. That is least significant 5 and the remaining 7. You got me? These least significant 5, you plot it in the final field. You will call it as a word field. And this remaining 7, you are going to plot it in the index field. This is how you are going to make a division whenever you are asked to find out the number of digits for the tag and index and the word. Okay. So here I just have to tell you one more thing. That is, this index can be called as an index or line or block field. These are the things that are mandatory. Okay, so sometimes you will be given a question that this is the cache size. It is either direct mapped or set associative map. And these are the number of digits that a CPU uses. And this is the block size. So every time what you have to do is very simple. First of all, you just draw a block diagram for the total number of address digits. Okay. And then you divide the address digits into index and tag. You know what is index? Index is equal to the number of digits that are needed to represent cache. Tag is the remaining digits. And when the block size is given, this index will again be divided into two parts. Number of digits that are needed to address block and remaining is index. Okay. In the previous case, block size is equal to 32. So the number of digits that are needed to represent a block is equal to 5. 5 must be plotted in the least significant field and 7 must be plotted in the index field. So this is how you are going to divide the index and the block, rather index, the word and a tag. Here you can understand that this least significant word field, is just nothing but block size. Okay, I hope you got it. So what you have to do is, you just go through all the questions which are based on the cache memory mapping techniques, such as direct mapping and set associative mapping. Okay, only the difference between direct and set associative is, in the set associative mapping, index is equal to index minus 1, tag is equal to tag plus 1. Hope you got it. Okay, so that's it for the day. Hope we meet next week. And in the next week when we meet, we're going to go ahead with the rest of the topics. That's it for today.